Hi, I'm Aaron Mishkin, and I'm going to talk about a recent work that I had at NeurIPS 2019 about making stochastic gradient descent painless for models that are highly overparameterized. This was joint work with Sharon Vaswani, Issam Laraji, Gautier Guidel, my supervisor Mark Schmidt, and Simone Lacoste-Julien. And I want to start with a quote that I saw in a recent ICML 2020 paper, which says that stochastic gradient descent is one of the main workhorses for solving large-scale supervised learning and optimization problems. If you're reading papers coming out in optimization for machine learning right now, you've probably seen a quote like this somewhere in an introduction because it's a pretty popular sentiment. A lot of authors right now are expressing this idea that stochastic gradient descent has become the main workhorse algorithm for large-scale machine learning. So perhaps you'll forgive me when I say that SGD is now the most popular algorithm for fitting machine learning models. I think that we should be familiar with this simple recursion that defines SGD. We just update the current model parameters WK by subtracting a stochastic gradient, f sub I, multiplied by some step size, a to k. Despite the simplicity of this algorithm and its long history dating back to the 1950s, practitioners in machine learning still face major challenges with speed, stability, and generalization. From an optimization perspective, SGD is actually a very slow algorithm because we typically need to use a decreasing step size or some sort of averaging scheme to ensure that we converge despite the stochasticity of the gradients. From a stability perspective, anyone who's tried to fit a large neural network using SGD knows that the step size hyperparameter needs to be carefully tuned to avoid diverging while also achieving as fast a convergence rate as possible. Finally, this issue of generalization. As a community, we're starting to understand that our choice of optimizer for overparameterized problems actually also encodes a choice of solution. This means that there are statistical trade-offs embedded in our choice of optimizer, so we have to think carefully when we pick SGD versus Atom versus Adagrad or some other stochastic first-order method. And so what I want to do in this brief talk is discuss how we can exploit the overparameterization of modern machine learning models to design better optimizers that are less painful for practitioners to use. What we have here is just a simple binary classification problem. We want to separate the red pluses from the green O's. This problem might be separable because we're in the large, highly overparameterized feature space of a big neural network. It might be separable because we're using overparameterized kernels and the data is separable in the Hilbert space. The important thing is, though, that when our data is separable, we can actually obtain much faster algorithms. If we were to run SGD as prescribed by the classic theory in this case, we would use a decreasing step size and slowly converge to the separating hyperplane W star. But if we were to use a constant step size, we would still converge because once we find a separating hyperplane, all we have to do is blow up the norm of the weight vector to push our cross entropy loss to 0 for every data point. And this is because every data point is being correctly classified. As the loss for every data point goes to 0, the stochastic gradients associated with those data points also go to 0, and so we have no need for this decreasing step size or averaging scheme in order to converge. We can formalize this using the notion of interpolation. So if our loss function is a finite sum function, meaning it's just the sum of a bunch of individual loss functions associated with the training points in our dataset, as is common for machine learning tasks, then we say that this problem satisfies interpolation if the global minimizer for our overall loss function is also a global minimizer for each of our individual loss functions. In the case of separable binary classification, this is pretty clear. Once we find a separating hyperplane, this is correctly classifying all the data points, so it's also optimal for all the individual functions. However, if our data is non-separable, there are always going to be some examples that we could have classified properly, but we didn't because we chose the best available hyperplane for the overall function. This means that those individual functions have better global minimizers associated with them, so we don't satisfy interpolation. When a function satisfies interpolation and our typical notion of Lipschitz smoothness, then we can derive a simple noise bound on the stochastic gradients. This noise bound just shows that as we approach the global minimizer of the overall function, all of our gradients are going to go to 0, and so we can converge without a constant step size. This or with a constant step size. This is exactly the behavior that we saw for our separable classification problem. And in this case, recent work has shown that SGD is actually nearly as fast as gradient descent. Nearly here means as fast up to constant factors. And we can also show that SGD converges to the minimum L2 norm solution for underdetermined linear regression. This is a result that we've known for a long time. A result that we have only learned just recently is that SGD will also converge to the max margin solution for separable logistic regression problems. So the takeaway here is that when our model is highly overparameterized and satisfies interpolation, not only do we get faster optimizers, but we can also understand some of the statistical trade-offs associated with our choice of optimizer. But if you're like me, and the first thing that you had to do when you started working in machine learning was run a grid search to pick the step sizes for stochastic gradient descent, you want to ask about stability and hyperparameter tuning. Are we still stuck with these grid searches for highly overparameterized models? And this is the question that we tried to address in our NURBS 2019 paper. The answer, of course, is no. You can do better than grid searches in this circumstance. So what we did was we returned to the classic idea of line searches from deterministic optimization. The basic plan here is to look along the direction of the negative gradient and pick a step size that ensures sufficient decrease in your function. In the deterministic setting, this is the Armillo condition. What we did is we just generalized this to the stochastic setting, and in the stochastic Armillo condition, we request sufficient descent on one of our stochastic subfunctions, f sub I. Geometrically, this looks like extending a hyperplane in the direction of our negative gradient and looking for a step size where the function value is below that hyperplane. Okay? And in this case, we can prove all sorts of nice convergence theorems. So we can prove that we get linear rates in the strongly convex setting, we get a 1 over t rate in the convex setting, and we get a 1 over t rate to a stationary point for non-convex functions. One thing I want to emphasize here is that you don't, in practice or in theory, need to know the Lipschitz constant or the strong convexity constant for any of these results, except for the non-convex case. In that case, you need to know the constants because you have to upper bound your step size in order for the theory to go through. In practice, we did not observe that that was necessary. And in practice, this algorithm works really well. This bright red line here from MNIST for CFAR 10 and CFAR 100 is just simple SGD with the stochastic Armillo condition. And what we see is not only does the algorithm converge very quickly without requiring any tuning, but it also gets better generalization performance than other modern optimizers. This better generalization performance calls back to this issue of understanding the different statistical trade-offs encoded by optimizers, and is something that we don't yet fully understand, but is clearly very interesting behavior. Thanks for listening to my talk, and I hope chat with you about this later.